So what I'm going to do is for lab tomorrow, we're only going to do the part with the scientific method. That is measuring the time it takes for freezing of salt water versus hot water versus cold water. So we're only going to do that for the lab, and then I'm going to go over every single question. And I want you to write down explanations for every single question and then turn in those explanations with your lab report on Thursday. And then I'm going to go through and see how people do with those explanations. And the reason I'm doing that is because I want students to learn. And there were some very common errors on things that I apparently did not teach adequately. Things like the right-hand rule. Almost everyone got the right-hand rule questions wrong, which results in nobody getting more than 75% on the knowledge section of the test. And, so I want to make sure we go through and we have those things straightened out so people have better understanding. So you still need to do the pre-lab quiz for lab tomorrow, and you're still going to do the part with the whole scientific method part is the only part we're doing. So it says in there, what the scientific method part is. That's the part we're doing. And I haven't tabulated, I've tabulated one person's score. One person got both of the questions that I had the right answer for the synthesis correct. And so that person got 80% on the test. Everyone else missed one or both of them. And so I need to go through and grade those by hand. So I don't even have scores for the other people because I haven't regraded by hand. I have a third of the class or so, but only that much. And yes, I want scores. I want people to learn more and then scores commensurate with that more learning. Andrew.
When we go through this stuff in lab, each
Yes.
question, and we turn that in, does that give us any credit? Or
Yes, it does. Yes. That's the other point. I said there are two reasons. I only gave you one because I want your learning. The other one is I want you to have scores that are reasonable. I mean, if everybody misses the same thing, I assume that must mean that I somehow didn't cover it the way I thought I had. We all straight? Leslie?
Will we go over the synthesis as well?
Yes, we're going to go over every problem on the test.
Awesome.
Okay, yes, Lydia.
So how much will that benefit us when you're grading? Will that...
Honestly, I have not decided that factor yet because I've only seen one person's overall grade from the first one because of the grading stats I'm at. So I haven't decided how much, but it will definitely improve people's scores. And it should be a fairly dramatic improvement in scores, I think. Okay, let's get on with the new material. So what did we do in class on Friday? We spent a long time what?
That was a long time ago.
Oh, that was a long time ago. Because we did spend a lot of time. I know students traditionally complain, you spend all this time on this and it's meaningless to me. But it's not meaningless, it's very important.
To be fair, it did take you a while to open up the notes.
It did. Just like it did this morning. Thankfully you weren't here. So what did we do on Friday? The what?
I can't
remember.
You covered ideal gases and all the different
Okay,
laws.
ideal gases and then the kinetic theory of was the thing that was the long derivation. Where I said, okay, I have a box, in the box I have ideal gases, so we had to define what ideal gases were before that. Bouncing around, then we calculated the average pressure on one wall due to one molecule bouncing around. And then we did a little statistics to change from using just the x component of velocity to the average velocity for all of the particles. And we ended up with a relationship that said, here's the picture we started with, here's where I wanted to go. Oh wait, we've already covered that, my mistake. Here, we we came up with this equation at the top that said the average kinetic energy was 3/2 PV over N. That was substituting the ideal gas law in at the end of our calculation. So the average kinetic energy is 3/2 kT. Using the ideal gas law was here. Going from here to here was using the ideal gas law. So average kinetic energy is indeed proportional to the temperature. Here's one more thing that I find really interesting. In physics, I told you that things naturally go to what kind of energy state? The lowest, right? Well, in a situation like this ideal gas, we say it has 3 degrees of freedom. A degree of freedom is a way it can have energy. And any normal person says, okay, the ideal gas here, well, there is gravitational potential energy, but we never talk about the gravitational potential energy for a gas. And so you just say, well, there's kinetic energy. Kinetic energy is a scalar, right? It only has magnitude, no direction. But in terms of degrees of freedom, we say that there are 3 degrees of freedom, 3 ways we can have energy. One associated with momentum in this direction, one associated with momentum in this direction, and one associated with momentum in this direction. And physics is going to try to go to the lowest energy state, which means it's going to try to evenly split the energy between all of those, so each one is at the bottom of the well. So we have this thing that's called the equipartition theorem. That says the energy is equally partitioned between all of the degrees of freedom, all of the ways that you can store energy. So now, I should have been a little more careful. For a single molecule, it has 3 degrees of freedom if it's an ideal gas. If I have 2 molecules, each molecule has 3 degrees of freedom, so that'd be a total of 6. If I have n molecules, then I'd have n times 3 degrees of freedom. And so this kT over 2, if I take this, we have 1/2 kT is the energy per degree of freedom. And so the kT, the reason we like to have the K next to the T all the time is because that kT has units of energy and gives us the amount of energy that goes in each degree of freedom. Yeah, question. Because there are 3 degrees of freedom for each molecule. And so it's 3 times, parentheses, 1/2 kT. Now, I just brought in this experiment so we can have fun and see that, what was it, Boyle's law? I don't remember whose law is which. Works. This here is a bulb that holds gas. I can release pressure just like you do on a bicycle tire here. So right now it's at 15 pounds per square inch is the pressure inside. What will happen to the pressure inside if I put it in this hot water? Okay, it should go up. Most of us just think of this, at least I just think of this as part of the ideal gas law. But you see what's happened to that needle? It's indeed going up, right? And if I take it out, it should go down. Now, what will happen if I release the excess pressure here? Okay, it'll go back down because, duh, you release the pressure. What else is it going to do? Now, what happens when I take it out of the hot water? Should decrease. It's not. Why not? Because it hasn't cooled down, exactly. We've got the gas in there and a piece of metal that's cooling slowly. If I put cold water on it, it should cool more rapidly. And we can see it going down a little there. So, just an example to show you those ideal gas laws in action. I will not ask you a question that says Boyle's law or Charles' law or Gay-Lussac law or Avogadro's law. Because you just combine all those together and what do you have? It's the ideal gas law. And you can just use the ideal gas law any place where you would have used one of those independently. Because those have the hold this constant in them. You can just hold that constant in the ideal gas law equation. It's off, but I'm going to pull the plug too. I know, I heated up water just for that. I just wanted to give you an example of seeing that. Okay, continuing on. I did the interlude there because it was hot enough to do it. We talk about the RMS speed. RMS means root mean squared, which is just the mathematical operation we've done. If I were to ask you for the average speed, let me back this up. The average velocity of molecules in this room, what would the answer be? Zero. The average velocity of the molecules is zero because I have as much going this way as that way, right? As much this way as that way, and so on. So the average velocity is zero. So there's no value to us in calculating the velocity. Because of that, I know I have the speed here. Speed is a scalar, but we calculate the root mean squared velocity. That is, we take the velocity squared, or the speed squared, because speed squared, you do velocity dot velocity and you get speed squared. And then we take the average, and then we take the square root. So that's the process of calculating RMS. Now notice the RMS. The last thing was the R. Mean was the middle thing. And square was the first thing you do. So the RMS has the order of mathematical operations reversed. Now really quickly, let's suppose that I had 3 particles with the following speeds. 1, 2, 3. Now the average speed isn't 0, right? Or the average velocity isn't 0. What's the average speed? 2. That was really high math, right? Pressed you or stretched you. Now let's do the speed squared because the first step in RMS is to square the speeds. So I do the speed squared, that's going to be 1, 4, and 9. Anyone who wants to correct me can. There should be units for speed and speed squared. I'm just doing it in unitless values to make life easy. So I have 1 plus 4 plus 9. Take the average of 1, 4, and 9. You add them together. 14 divided by 3. 14 divided by 3 is 4 2/3. Or 14/3 if you want to leave it in fractional form. And so that's the average of the squares, right? Root mean squared. Squared it first, then did the mean, 14 over 3. Then finally you square root it. So what's the square root of 14/3? .16. Note important outcome, the whole reason to do this little calculation. The RMS speed is not the same as the average speed. It's the average of the squares and then square rooted. And it will always be greater than or equal to the average speed. The only case where it's equal is if it's all the particles have the same speed. You know that's not going to occur, right? So taking out that case that can never occur, the RMS value will always be higher than the average value. Another important thing here, I can take this relationship right here and this relationship here, 1/2 m v squared average is equal to 3/2 kt, and that means I can calculate the RMS speed for any molecule based on its temperature. For any molecule, I can just solve that for the, remember the greater than, less than signs is our way in physics of saying average. So the average of v squared is equal to 3 kt over m. What is m? You can go with one-word answer that's imprecise. What's the one-word answer that's going to be imprecise? Mass. But the problem is mass of what? Mass of a particle or a molecule if you're dealing with molecules. So that M is the mass of a molecule. And so it's going to be like, what is the mass of a molecule of helium? Let's go with a monatomic ideal gas. Well, that's 4 atomic mass units, or 4 grams divided by Avogadro's number. So that's going to be a really small mass. It's the mass of a molecule. It's easy to make mistakes and trying to put the mass in grams and get the wrong answer. Well, the mass in grams. You want it in kilograms, but the mass of a mole instead of the mass of a molecule. And so if I wanted to get the VRMS equals the square root of that, which would be the square root of that. So the RMS speed is proportional to the square root of the temperature. This becomes important in things like, well, let's talk diffusion. Diffusion, if I broke open a little vial of perfume, like Mary did to wash Jesus' feet, that smell doesn't get to you instantly. In fact, Ron White has a good little comedy thing about an airplane traveling faster than the speed of smell. We have diffusion of the gases. And that diffusion of the gases can't go faster than the speed of the molecules themselves. And so you can get a back of the envelope calculation on how fast a smell will move through a room or a gas will move through a room. If we're MacGyver and there's poison released in the back corner, I know how many millionths of a second I have to get out of this room by just using this calculation and saying, okay, temperature in this room is, what units do I have to have? Kelvins. So it's roughly 300 kelvins. And K is 1.38 times 10 to the minus 23rd. M for this bad boy is this many kilograms. Multiply by 3, do the square root, and you get the speed. And the speed of molecules is going to be on the order of 100 or so meters per second. It depends on the molecule. Some will be much faster. Another thing this makes a difference for is for things like shooting a gun. My master's degree research was in shock dynamics, where I had a piece of sapphire crystal and a piece of sapphire crystal. I made them hit each other at speeds of like 1 kilometer per second. So how do I make them hit each other at a speed of 1 kilometer per second? We had a 4-inch artillery cannon, and we fire them down there. And we didn't use explosives, trying to avoid anybody saying you're military. We used high-pressure gases. And usually, we use high-pressure nitrogen. Why would high-pressure nitrogen be a good choice? It's not dealing with the periodic table. When I go to helium, that will deal with the periodic table. Why would nitrogen be a good choice for my propellant? What is air? 79% nitrogen. So I'm basically using dry air. That's what, if you go to Costco and get your tires, they fill your tires up with nitrogen instead of air. The point is, not having water in there keeps your little temperature sensors from getting damaged by water and corrosion. That's really the advantage of the nitrogen gas. For high-speed shots, though, instead of nitrogen gas, we use helium gas. Now you look back at the periodic table. Why is helium gas preferable to nitrogen gas for high-speed shots? It's a lighter gas. And so a lighter gas is going to have a higher RMS speed, which means that when you release the gas to push the shell, the gas molecules can chase the shell at a higher speed and keep pushing longer. And thus you get the shell going at a faster speed. Of course, this has some negative things too. Helium gas. Our technician was worried about our putting helium gas into the atmosphere. Well, the Earth doesn't have much helium in the atmosphere, but it produces a lot of helium. We produce helium because of radioactive decay. Uranium decays through a long chain that produces something like 8 or 9 helium atoms before it becomes lead. And so the Earth is constantly producing more helium gas. But the Earth can't hold on to helium gas. The speed at which the helium gas is traveling is fast enough for it to break free of the Earth. Now, I said speed is 100 meters per second. Maybe I was underestimating, because the speed on the surface of the Earth necessary to break free is 11.2 kilometers per second. And the speed of helium gas at room temperature is about that fast. So helium gas can escape from the Earth. Hydrogen gas can escape from the Earth. So we have helium and hydrogen, mostly because the Earth is producing these through radioactive decay. So all of that has to do with this calculation for RMS speed as a function of temperature. Which kind of energy is proportional to the temperature in an ideal gas? In an ideal gas, that proportionality was pretty clear. Which one? The total kinetic energy. Yeah. Don't be all surprised. Been learning things, right?
Yeah.
Now for some statistics. I know that there is one young man who's been learning to do a lot of summations in his Calculus 2 class. Trace has also been doing it, and Michael's been doing it. And Nathan asked me, what's the point of this? Well, and I told him, thermodynamics uses it some. And here's an example. The Maxwell-Boltzmann distribution for gases. Maxwell-Boltzmann, two different dudes, did calculations about the distribution of speeds you should have in a gas. And so they applied statistics, which may require them to do things like the summations you're learning to do, to determine what the distribution of speeds would be. And they came up with this equation you see up there at the top. The probability of having speed v is equal to, and it actually is having speed v between v and v plus delta v. Is proportional to, you see that m over 2 pi kt to the 3/2 power. Well, now we know that that has something to do with speed, right? Because the m square root of 2 kt over m was the speed. So that's 1 over pi cubed times 1 over the RMS speed cubed times 4 pi speed squared. That's not the RMS speed, but the speed itself. E to the minus kinetic energy over kT, which gives us speeds that will have a higher peak speed if it's hot, a lower peak speed if they're cold, and a distribution of speeds. Now, I should point out that this is done assuming that speed can go up to infinity. We know that speed can only go up to the speed of light, but within pretty good approximation, it's still the correct equation. And from that distribution, then, we can find the most probable speed. The most probable speed is not the average speed. It's if you were to measure a whole bunch of particles, enough to get multiple speeds of the same one. The one you'd find the most particles at the speed would be the most probable one. So you see V sub P is marking the most probable. And using that Maxwell-Boltzmann distribution, as we're going to do in class tomorrow, calculus students. Actually, yeah, we'll do it tomorrow. What can you tell me about the slope that tells us where the most probable speed occurs? Just giving those students prime. What's the slope when I have the most probable speed? 0. So you just find where the slope is 0. People in calculus class, what does that mean? Slope is C. The derivative, my friends, the derivative. That's why I was only pointing to calculus speed for that. So you just set the derivative of the distribution with respect to speed equal to 0, and you find it. Then we have the average speed. The average, just like for the test, I take the number of people who got this score times the score plus the number of people who got this score times the score, add them all up, divide by the total number of people, that gives me the average. We do that with this distribution. We take the height multiplied by the speed, add those all up, calculus people, how do we add them all up? If it was discrete summation, but it's not discrete, so we integrate. That's right. I wasn't even somebody in calculus who said that. So you integrate that, and you find the average speed. And notice the average speed for a Maxwell Boltzmann distribution is 13% higher than the RMS speed. So if you have a standard gas with nothing special going on, the average speed is always going to be 13% higher than the most probable speed. And then if you calculate the RMS speed, well, you have to take the speed squared times the distribution, integrate it, and then square root. You find that the RMS speed is 22% higher than the most probable speed. So there's easy, I say easy, simple as long as you can do the math, ways of getting the information out of this Maxwell Boltzmann distribution. We're going to come back and I'm going to just move on. We're going to come back and talk about that right now when it comes to evaporation. Evaporation is the process of a change in phase, of going from the phase of liquid to the phase of vapor. And in class I said before that in a liquid the molecules are free to move around each other, but they can't break free of each other. But if the molecules are going fast enough, in terms of temperature, what does it mean if I say they're going fast enough?
High enough temperature.
High enough temperature. So the molecules have a high enough temperature, they can break free. They have enough energy to break free. So this is on a molecule by molecule basis. But from that Maxwell Boltzmann distribution, we could say, okay, boiling temperature is here. Any molecule that has an energy on this side of that line can break free. Now I know that had speed, but you can go from speed to energy, right? So if I look at the green line, there's a real big chunk of molecules, a fairly large percentage of the molecules that will have a high enough energy to break free. Where if I'm at the lower temperature, the red line, I know these colors don't match. The red line only has this amount that has enough energy to break free. So the green line, that temperature would have a lot more evaporation going on than the red temperature would. So higher temperature stuff will evaporate. Of course, if I take away the highest energy particles, what's the average going to do? It's going to drop, right? If I had 1, 2, and 3, and I took away the 3, the average would go from 2 to 1.5. So the average drops, which means the temperature drops when we have evaporation. So evaporation is a natural cooling process because the high energy, the high temperature molecules are the ones that evaporate, leaving behind the cold ones. Now, this picture here shows one container open and one container closed. If the container is closed, molecules that evaporate come back and hit the material and go back in. And so they bring their energy back in. So what's the average change in temperature going to be for the fluid if you have all of the molecules evaporate come back in? It's not going to change. It's going to stay the same. So if I have an enclosed fluid, I'm not going to have an evaporative cooling because the same amount of energy is coming back in. And the water level is not going to drop because I'm not losing on it. If it's open, then I'm going to have some of them will come back, but most of them won't. And so in that case, I'm going to have cooling. Now, we probably all know if it's a hot day, you're out at the, let's say, a lake because we're far away from beaches where we should be on hot days. So you go to a lake on a hot day, and if somebody splashes you with water, you feel cold. Why do you feel cold when somebody splashes you with water? Okay, the water may be
Sucking
cold.
your heat from your body.
Okay, so heat goes out of your body into that water. And then if a breeze blows, then you feel what? Really cold. Because the water that evaporates off of your skin is going to be carried away by the breeze and not going to have a chance to return. So you're going to have virtually no return energy from any energy that leaves you through evaporation. And so if you have a fan blowing on you and you're wet, you're going to have much more evaporative cooling because the hot material that left you is going to be taken away and not have a chance to come back. So if you live somewhere, okay, one more thing on this. If you live somewhere dry, like Arizona, anyone here from Arizona? Yeah. Okay. You are? Yeah, Lewiston.
Well, born in Arizona.
Oh, okay.
First time being born there.
And Michael's lived in Arizona for at least 3 months. In Arizona, swamp coolers are really popular. You guys know what a swamp cooler is? Okay, some people do, most people don't. A swamp cooler, you just run water over some pipes. So you take air out of the house, you run it through these pipes, and you run water over it. Why does that work? You run the water over it, the air from the house is warm, goes in the pipes, makes the pipes warm. The warm pipes then heat up the water evaporates, takes off energy, and then draws more heat out of the pipes, and that's how you cool. It's very effective in Arizona because Arizona has a low relative humidity. Humidity is a measurement of how much moisture is in the air. Relative humidity is how much moisture is in the air divided by the maximum amount of moisture the air can hold. If the relative humidity is 100%, you can't put any more moisture in the air. It's 50%, you can put a lot more in. So if I have a cup that's open to the atmosphere and it's 100% relative humidity, I'm going to have as much water molecules coming into the cup as I have leaving. And so my net evaporation is going to be close to zero. And this works in Nebraska. You can put a cup of water in your house and leave in the beginning of June, come back in August, and that cup is still going to be pretty full. Whereas if you go to Arizona, no, it is true, I did it. Not intentionally, but if you go to Arizona, you don't have that happen. My wife's stepmother lives in Arizona, and they have buckets of water they leave everywhere in the house when they go to Minnesota for the summer. Because Arizona in the summer. Not the happiest place to be as far as temperature. There are lots of good things there, mind you. And so they have buckets of water to try to keep the relative humidity in the house from dropping down to, less than 10. Because that dries out lots of things that we don't want dried out in our house. Okay, I've got to move forward. I am taking too much time. PV diagrams. How many people have seen a PV diagram? It's not the common one we see. We usually see a pressure-temperature diagram, but the PV diagram is showing for a material the pressure on the vertical axis, the volume on the horizontal axis. So if you compress it, the volume will get smaller. So there's a pressure kind of built into this, but it doesn't show it directly. And then for different temperatures, you can have a material follow the line. So at high temperatures, if the volume is low, then you're here, and if the volume, or large, you're here, and if the volume decreases, you go here. And notice that at that temperature, there is no possibility of hitting the liquid phase, which is marked in blue. So there's some temperatures where you simply can't have a liquid. And if you are far away from the point of liquefaction, then we can treat it as an ideal gas. So the line I drew should be obeying the ideal gas relationship, which says PV equals nRT. So if temperature is constant, actually it does have pressure. If temperature is constant, then P is equal to nRT, a constant, times 1 over V. And so that's a 1 over V relationship that's being plotted. But if you get close to the temperature where it can become a liquid, you see it changes and doesn't follow that at all. So this shows us a nice way of seeing where it's ideal, where it's not ideal. Here's what we call a phase diagram. Pressure versus temperature. This is much more common. Pressure versus temperature. Vertical axis is pressure, horizontal axis is temperature. And we have this interesting shape. Notice water is on the left-hand side, carbon dioxide is on the right-hand side. They don't look the same. Water is an unusual beast. What's unusual? Well, first of all, at really low temperatures, we can have either a solid or a gas here. Now, that's from what we have plotted. But you can't have a liquid. Does that make sense to you? Right, it should for most people. Our experience is if I have water and I cool it enough, it becomes a solid. It's no longer a liquid. The thing that's interesting is as you change the pressure, there's no pressure that's going to allow you to have liquid once you get below a certain temperature. This temperature right here is called the triple point. At that temperature and that pressure, only at that temperature-pressure combination, you can have all three phases, liquid, solid, and gas. That's used as a reference point for calibrating our temperature scales because it's only one point. There's no other, no situation where you can have pure water in all three phases except at that temperature, at that pressure. 0.006 atmospheres and 0.01 degrees Celsius. So that's called the triple point. Out here, the critical point is the highest temperature where you can distinguish between a liquid and a gas. Now that sounds weird. In my astronomy class, I try to explain this. If you fall into Jupiter, the gas gets thicker and thicker and thicker, and at some point you'd say, this is totally liquid. But at no point would you have said, I just went from gas to liquid. Because it just continued to get thicker. There was no phase change. So you can go, a standard thing that you do in life is you take water at 1 atmosphere and you heat it up from room temperature to out here, and you notice it's liquid, now it's boiling, and then it's, hey, I wasn't supposed to erase, and then it's a gas. Very clear distinction. But you could have taken that same water and you could have raised the pressure up here, raised to, 250 atmospheres. It's pretty high pressure. Then you increase the temperature. Then you lower the pressure back down to atmosphere. And then you lower the temperature. And you have the same ending point. It's in the same situation, but you never saw the water boil. You never saw the water change from liquid into gas. It just got thinner and thinner and thinner. Which I find really bizarre, that you can go from this state to this state, go by one mechanism, you'll see a change from liquid to gas, go by another mechanism and you won't. Now, I haven't talked about the thing that's different about these. I've talked about things that are the same.
Would that be because if you raise the pressure, the change would be more uniform?
No, it's simply because you don't have, remember, to have a solid to liquid is a lot easier to understand. A solid phase, they're all bound into specific positions. Liquid phase, they're free to move, but they're bound together. Liquid, they're free to move around each other, but they can't escape. You heat it up, you increase the pressure, and you don't see any difference in terms of they all of a sudden started escaping. But you've gotten to the point where they're so separated, well, actually not so separated in this case because the pressure is they're so compacted that you can't really tell. Then you raise the temperature, they stay compacted. Then you lower the temperature, and they're going to expand, but they're not bound together at this point. And so you never see it changing. Okay, so you have a triple point and a critical point for both liquid water and carbon dioxide. But this line here is the one that is different for the two. Carbon dioxide is normal. It's normal. If you raise the pressure on carbon dioxide, it's more likely to be in the solid phase. That makes perfect sense because solid phase, each molecule has its own position. You compress things, they're more likely to be pushed into their own position instead of wandering about. But water is just the opposite. Water at low pressures, if you compress the water, it actually melts. The molecules are less likely to stay in their own position, more likely to break free. That's really bizarre, and that's why water expands when it freezes. And if you compress it, you'll melt it. That's really important. Without that, we have no life on Earth. Why? Well, here's one of the problems if water was normal. We have lots of water on the surface. Let's say you live up in Minnesota. It gets cold. The water on the lakes freezes. Where's the frozen water? It's on top. You have frozen water on top, and that frozen water forms an insulator, something that makes heat travel more slowly, which is the topic du jour, should we get there in the last 5 minutes. Makes the heat travel more slowly. So you insulate, and the temperature under the top of the lake can be warmer. It stays liquid, and fish can swim and live. If, when you froze water, you make little ice crystals and they sink, then when it gets cold, you would have ice form go to the bottom of the lake, more ice form on top of the bottom of the lake, and your lakes would freeze solid from the bottom up. Right? From the bottom up because ice crystals would sink to the bottom. And so then we have frozen lakes. The lakes would be colder, take longer for them to warm back up in the summertime. It would lower global temperatures. We'd become ice cube-ish. So we need water to have this effect just to live and stuff. Okay, let's forget that. I'm not even going to talk about boiling because I want to talk about the states of matter. I should continue on with the relative humidity. One thing I didn't state, the amount of moisture that air can hold is a strong function of temperature. At low temperature, air cannot hold much moisture. Hence, cold air is fairly dry air. Higher temperature air can hold much, much more water. So when it's hot, the air can have a lot of moisture in it. This graph here on the right shows the saturation vapor density, how much water vapor the air can hold as a function of temperature. And notice it's logarithmic. So at minus 50 degrees Celsius, you have that saturation vapor density is about, let's say, 0.04 grams per meter cubed. And if you go up to plus 50 Celsius, it's around 90 grams per centimeter cubed. Holds much more moisture. That is important for things like, deserts. Of the heating types, there are 3 types of heating. The first one is direct contact conduction. And I guess on Wednesday I'll go through the equation on conduction because I clearly don't have time for that. But conduction is direct contact heating. Then the second one is convection. Convection is an intermediary is taking the heat. So my wife got a convection oven this year and she loves it. She makes wonderful food for me. The convection oven has a heating element and then it blows hot air onto the food. The blowing hot air means that air is transporting the heat from the heating element to the food. Now, natural convection occurs quite regularly. If you drink coffee and you put creamer in it, the creamer will form convective cycles where you have creamer on the top, is cold, but then it sinks down, gets heated up, floats back up again because when it's heated, it expands and becomes less dense. We have that kind of thing happen in the Earth. At the equator, it tends to be hot. And there tends to be a lot of water at the equator. So you tend to have hot air that picks up a lot of moisture from the water. But hot air is going to expand. And as it expands, it becomes less dense than the air around it, so it rises. That's the beginning of our convection. We have hot air rising. But as it rises, the pressure drops, right? Because you have pressures due to the weight of the air above you. As the pressure drops, what results in a gas? Heat equals nRT. If the pressure drops, what's going to happen to the volume? It's going to expand, right? And as it expands, it also cools. And so that hot air is going up and it cools. But if it's cool, it can't hold as much moisture. And so it drops the moisture. So you have rain. So the hot air rising will drop water. Hence, rain almost every day in Hawaii, right? There's some places that it pretty much rains every day there. Because you have hot air, hot moist air rising. So then it gets up to the high altitudes. Now it's cold air. It went up because it was hot and it started its upward motion. Stayed hotter than the air around it, continued its upward motion. Now you have cold, dry air up at the top. Now if you come up at the equator, the air is going to go north or south, depending essentially on which side of the equator it came up. Air hardly ever crosses the equator. It just comes up and goes back to its own side. Now it is going to have the Coriolis effect occurring as it goes to its own side, so it changes its direction a little bit. Then it's cold, so it falls back down because it's now cooled off, so it's less or more dense than the air around it. Falls back down. So now you have cold, dry air coming back down. But as it comes down, the pressure is increasing. As the pressure increases, what happens to the temperature? It goes up. Right? Pressure increases, it gets compressed, and the temperature goes up. And so it comes down and hits the ground as a hot, dry air. Dry air because it was dried on the way up. Well, hot, dry air coming down is going to make so you don't have rain, hence that makes deserts. And so deserts tend to be about 30 degrees north and south of the equator because of these convective currents of air. Which is very cool, I think. We can understand basic things about our world through physics. So, once again, skipping over that, the three methods we talked about: conduction, direct contact; convection, that is a fluid such as air or water transporting heat; and then we have radiation. Radiation is electromagnetic rays. That's how we get energy from the sun. Right? We don't touch the sun. We're not conducting. We do have a solar wind, particles from the sun that reach the earth. So there is a small amount of convection, but the vast majority of the energy we receive from the sun is radiation, what we call light. Light is a form of heating. And so, as you may know, my wife does this every winter. She'll go curl up like a cat under the window, so she's heated up by the radiation coming from the sun, by the light. Okay, we'll end there. I'll see you in lab tomorrow. Make sure you bring paper and pen to write down test problems.
And then we'll have our test score then to see which ones you missed. Do you want us to do all of them, or do you just want all of them? So it's not just the ones you missed.
That's right, all of them.
Oh, okay. Awesome.